Imagine a force that can lift tons of metal, generate electricity, or even levitate trains. This invisible power, fundamental to modern technology, often originates from a deceptively simple device, the electromagnetic coil. It's where electricity meets magnetism, creating a synergy that drives our world. Our journey begins with Hans Christian Ørsted's accidental discovery in 1820. He observed that an electric current flowing through a wire deflected a compass needle, revealing a profound connection between electricity and magnetism. This pivotal moment laid the groundwork for electromagnetism. André-Marie Ampère soon quantified this relationship, formulating Ampere's law, which describes the magnetic field produced by an electric current. An electromagnetic coil is essentially a conductor, typically a wire, wound into a helix or spiral. When an electric current passes through this coiled wire, it generates a magnetic field. Unlike permanent magnets, the strength and presence of this magnetic field can be precisely controlled by varying the current. The magnetic field lines around a straight current-carrying wire form concentric circles. When this wire is coiled, these individual circular fields combine and align. This alignment creates a much stronger, more concentrated magnetic field running through the center of the coil, resembling that of a bar magnet. The core of an electromagnetic coil significantly influences its performance. An air core coil, with no material inside, produces a relatively weak field. Introducing a ferromagnetic material, such as iron or steel, into the core dramatically amplifies the magnetic field strength. This is due to the material's high magnetic permeability. Several critical parameters dictate the strength of the magnetic field produced by a coil. The number of turns in the coil is directly proportional to the field strength. More turns mean a stronger field. The magnitude of the current flowing through the wire also directly impacts the field strength. The length of the coil inversely affects the field density. A shorter coil with the same number of turns and current will produce a more concentrated, stronger field. Finally, the permeability of the core material, denoted by mu, is a crucial factor, as ferromagnetic cores can increase field strength by thousands of times. Solenoids are perhaps the most common type, characterized by a cylindrical coil of wire. They produce a nearly uniform magnetic field within their core, making them ideal for applications requiring linear motion, such as in valves or relays. Their field is strongest and most uniform along the central axis. Toroids are coils wound into a donut shape. This closed-loop geometry effectively confines the magnetic field entirely within the coil, minimizing external flux leakage. Toroids are widely used in transformers and inductors, where low electromagnetic interference is critical. Helmholtz coils consist of two identical circular coils placed parallel to each other, separated by a distance equal to their radius. This specific arrangement creates a highly uniform magnetic field in the region between the coils. They are invaluable in scientific experiments requiring precise magnetic field control. Electromagnets are coils designed to produce a strong magnetic field when energized, often with a ferromagnetic core. They are temporary magnets, meaning their magnetic properties can be turned on and off. This controllable magnetism is fundamental to their widespread utility. Electromagnetic coils are ubiquitous in modern technology. In electric motors, coils interact with magnetic fields to produce rotational motion. Generators, conversely, use coils moving through magnetic fields to induce electric current, converting mechanical energy into electrical energy. Transformers utilize two or more coils, typically wound around a common core, to efficiently transfer electrical energy between circuits at different voltage levels. This principle is essential for power transmission and distribution. Inductors, single coils designed to store energy in a magnetic field, are vital components in filtering and tuning circuits. Beyond these fundamental applications, coils are integral to advanced technologies. Magnetic resonance imaging, or MRI, employs powerful superconducting coils to generate strong, uniform magnetic fields for detailed medical imaging. Particle accelerators use precisely controlled magnetic fields from coils to guide and accelerate charged particles to incredible speeds. Maglev trains achieve levitation and propulsion through the repulsive and attractive forces generated by powerful electromagnets interacting with coils embedded in the track. Induction heating systems use coils to generate eddy currents in conductive materials, producing heat for various industrial processes. Inductance is a fundamental property of coils, quantifying their ability to store energy in a magnetic field and oppose changes in current. Self-inductance describes a coil's opposition to current changes within itself, while mutual inductance describes the magnetic coupling between two coils. Eddy currents are circulating currents induced within conductive materials by changing magnetic fields. While often undesirable due to energy loss, they are harnessed in applications like induction braking and heating. Hysteresis refers to the lagging of magnetization behind the applied magnetic field in ferromagnetic materials, leading to energy losses in AC applications. The Q factor, or quality factor, of a coil indicates its efficiency. It is the ratio of its inductive reactance to its resistance, representing how well it stores energy compared to how much it dissipates. A higher Q factor signifies a more efficient coil, crucial for resonance circuits. Designing an effective electromagnetic coil involves careful consideration of several parameters. Wire gauge selection is critical as it determines current capacity and resistance. Insulation type ensures electrical isolation between turns and layers, preventing short circuits. Cooling mechanisms are often necessary for high-power coils to dissipate heat generated by resistive losses. Core saturation, where the ferromagnetic core can no longer increase its magnetization, limits the maximum achievable field strength and must be accounted for in design. Safety is paramount when working with electromagnetic coils. High currents can pose severe electrical shock hazards. Strong magnetic fields can interfere with electronic devices, pacemakers, and even cause physical injury by attracting ferromagnetic objects. Proper shielding and safety protocols are essential. From the simplest relay to the most complex particle accelerator, electromagnetic coils are foundational components driving countless technologies. Their ability to precisely control magnetic fields through electrical currents has revolutionized engineering, medicine, and scientific research. Understanding their principles and applications is key to unlocking further innovation in our increasingly electrified world.